Today we're going to look at how a DBMS evaluates queries and go into some of the details about how it makes the decisions it makes when processing the commands you type. So SQL, just like any programming language, is a good human-level description language, but it's not good at telling the machine exactly how to do what you want to do. So for example, you can write a query with a bunch of joins in it in any order, and you're not telling it what order to do the joins in. It's free to make its own decisions about how to do those joins. Just like in a programming language, you could write a for loop, and you're not telling it exactly what instructions to issue, like put a branch here and a compare there. It's free to kind of make its own decisions about how to do what you want it to do. So in a DBMS, you can kind of think of it like a compiler. When we execute a query, it has to translate that query and optimize it and figure out how to execute it. And the result of that is called a plan, rather than like an assembly program or a machine language program. So the process of translating an SQL query into a plan is first we just parse and translate it. Figure out the keywords, join, where, and so on, which tables, which columns are involved. And then there's an optimization process to figure out how to execute your query efficiently, and then it executes it. So let's look at translating SQL commands into a plan in the context of relational algebra. So it'll be kind of abstract and not necessarily exactly what's going on in a DBMS, but just to give us some basic idea. And for now, assume that there are no indexes in these examples unless specified, because which indexes exist are going to greatly affect the optimal plan that the system will pick. So we'll see after we add an index here or there how the best plan will change. So let's look at a simple example from the chess database. I want to find the result, or in other words, the winner, of all games on this certain date. So since the result is in the games table and the dates are in the events table, we need to do a join. So I have games join events, and then the on condition is just where the EIDs match. So it's like a natural join. And there are lots of different ways you could do this. If you think about this in terms of relational algebra, there's a join, there's a select, there's a project, and there are different orders in which we can do those things. So let's look at one of them. We can do the join first. So we look at every row in games and compare it with every row in events and find the ones where the EIDs match. The result, so the output of this here, will be a temporary relation, and we input that temporary relation into the filter, the selection filter. That's where we remove the rows where the dates don't match, and then the output of that goes into a projection to get out just the result column. Okay, here is another way we could process this query. We could start with just the events table and filter out the events that took place on that date. And there's probably only one of them, or maybe two, but a very small number of them. Then the output of that temporary relation is a very small relation, and we can join that with games. So then we look through every games, compare it to only a very few number of already filtered events in order to get this temporary relation, and then project out the result. And the DBMS does actually look at multiple options like this and picks the one that's likely to be the fastest. It can't always prove which one's going to be the fastest, so it uses heuristics to try to determine with a pretty high level of confidence which one is probably going to be the fastest. In this example here, hopefully it's obvious which of these two is going to be faster, but let's plug in some numbers and see what actually comes out. So let's say there are 100 rows in the events table, and 2 of those events are on the specified date that we're filtering by. There are 1,000 rows in the games table, and 5 of them take place at one of those 2 events. So they take place on the specified date, but the games table doesn't have date information, so we're going to need to do a join in order to figure out which those 5 games are. So the first plan, where we do the join first, we're just trying to find all combinations where the EIDs match. So we have to look at every row in the games table, then look at, for each of those, look at every row in the events table. It's like a nested for loop. And it's just size of games times size of events. So 100,000 rows accessed in order to compute that join. So the output of the join, this temporary relation here, only holds the rows where the EIDs matched, though. So that's just going to be 1,000 rows. It's the same size as the games table. But now we have the row from the games table and the row from the events table, so now we have date information. So we pass that into the next step, which is the date filter. And since we have no index, we have to just look at every single row in that temporary relation. So we look at 1,000 more rows in order to find the ones on that date. And then, as I said up here, 5 of them are on the specified date, so 5 of them make it out of that filter. And then when we do the projection, we have to look at those 5 rows. So about 100,000 total rows in order to process the query using this plan. Now let's look at the other plan option, where we filter out based on the date before doing the join. So if we're just looking for the events that took place on that date, we're only filtering on the events table, which has 100 rows, so we access 100 rows to do that filter. And then, as I say up here, only 2 of them are on the specified date, so the output, this temporary relation, is going to be 2. And then we do the join. And the join works the same way, where we're finding all rows where the EIDs match, so we still have to look at all combinations. So it's going to be size of games table times the size of the pre-filtered events table. So it's 1,000 times only 2 this time, so we look at 2,000 more rows to do the join. Pass that into the projection, and as stated up here, there are 5 games where those EIDs are going to match, 5 games that took place at one of those 2 events. So we do a projection on just 5 more rows. And the total now is about 2,000 instead of the other plan, which was about 100,000. And that's just because we did the date filter before doing the join. So the join had to look at fewer possible combinations. And remember that all of this so far is assuming that there are no indexes that will speed up any parts of either of these plans. But what if there is an index on events.date? Then doing this events filter in the plan on the right, we can use the index to filter out just the ones that took place on that date. So instead of looking at 100 rows, we look at log of 100 rows, a very small subset of the total rows. This first plan on the left, even if we had an index on events.date, we're doing that filter on a temporary relation, which was the output of this join. So that temporary relation does not have an index on date, so it still has to do a linear scan over all of those rows in order to find the dates we're looking at. So the order of operations, or the plan that you pick, you also have to take into account where indexes are and which parts of the query an index will help. However, even with this index here, it's not making that big of a difference. The much bigger difference came from doing the join after the date filter. So if we go back and look at this rough approximation of how many rows are accessed, in order to do this date filter without an index, we had about 100 row accesses. If we did put an index on here, we won't have to look at all 100 of those rows. Let's just say, as an estimate, let's say we have to look at 10 of them. Then this goes from something like 2,105 to about 2,015. So less, but really not that big of a difference. And if we go back to the first plan that was doing the join first, it was looking at about 100,000 row accesses. So the much bigger difference came from just rearranging the operations of the query and doing the join after the filter. So the joins are typically where most of the time is spent in evaluating a query. So there are indexes that we could potentially use that would help make this join faster. And we could put an index on maybe one of these EID columns so that we don't have to look at 2,000 rows in order to evaluate that join. And we'll look at joins in the next video.